Thank you very much. I really appreciate the opportunity to speak to you all today. Our team has been working on this software for more than 7 years now, and so it's a very exciting time to be releasing it as open source software and sharing it with the world. So the talk today is really, so I'm presenting on Quine. We'll go over what Quine is and how it works. Talk about the new capabilities that it creates for data pipelines and working with data, and where it fits in. So let's dive right in and talk about Quine with this first question: what is Quine? So we have to start in a certain kind of circumspect place here. For us, for our purposes, Quine is a streaming graph, but Quine also means a few other things. You might know the word Quine in computer science as a program that outputs its own source code. So any program that you can write that is a little bit clever and can output its own source code, that is a Quine, named by Douglas Hofstadter in reference to the 20th century philosopher, Willard Van Orman Quine. So this reference goes both ways for us. Both the Quine, the program that outputs its source code, and Quine, the streaming graph, are both named for the 20th century philosopher. In a lot of ways, Quine was kind of the godfather of functional programming, at least in my mind, and that has helped influence and shape a lot of what we did in the process of creating the streaming graph that we'll talk about today. So first, let's look at kind of the world today of streaming data. The goal of data pipeline engineers, data engineers, even data scientists who are working with data coming through their systems is really to take the data that usually comes in a high volume from lots of different places and interpret it so that you can get whatever the business value is out. And the real work is in this centerpiece. How do you interpret that streaming data? Take it in, understand what it means, turn it into the business value that you're trying to get out. So let's write some requirements for that process. We want this to accept a high volume of data, to have really low latency with how fast it runs and how it operates. We have to work with a limited amount of RAM that starts to get pretty expensive when you buy those heavy RAM filled machines. And it usually forces us into this trade-off of saying we can put data together if it arrives within certain time windows, then we can join it. But if it falls out of those time windows or one of the pieces we need arrives too late, then it becomes a little more problematic. It tends to require engineers to kind of turn the database inside out. I mean, take all the detailed information usually wrapped up in a database and expose it through the microservices that get spread out across a data pipeline. That means they have to confront these CAP theorem trade-offs and very fundamental issues that are now distributed across the microservice architecture. And it requires a significant amount of expertise, and it's very error-prone along the way. You probably have to figure out what it's going to be like to have distributed transactions through your microservice architecture, and how to handle this order-dependent processing where you can guarantee that some data is going to be ready by the time another part of the pipeline needs it. And then when all that is said and done, you need a way to go back and replay some data, probably by setting up a completely separate pipeline to re-ingest data from a certain time period so that you can maybe debug something or produce a report from last week. And so a completely separate pipeline gets set up to do that data replay. The end result of this is that stream processing, which started with this easy goal of take data, interpret it to turn it into business value, becomes very hard and turns into a giant tangle of microservices. The current state of the art is teams of dozens and dozens of engineers get put together to build a data pipeline like this. So each team is usually responsible for a certain section of the microservice architecture. They build it, they scale it independently, usually using lots of different languages, lots of different technologies. And that can work. It is technically possible to make that happen. And there's been some pretty heroic efforts by data engineers over the last 10 years to build the backends for the services that really power everything we know about high volume data processing. So all the big services online are backed by these kind of microservice architectures. And behind the scenes, they just require a huge team of people to build them, to maintain them, to keep them updated. And we appreciate their work and owe them a debt of gratitude, because this has been the state of the art. But the truth is that after a whole lot of pain and wrestling through this, we know that it is hard to build these systems. It's very error prone, it's slow. It usually takes anywhere from 9 to 12 to 18 months to put this together for the first time. Requires a lot of people, and it's very expensive. It's hard to hire those people. And if any of them leave, then you're probably better off just starting from scratch, because there tends to be a whole lot of implicit expectations around those systems in the back end. But this is the state of the art, and this is where we've been living for a long time. This world of microservices gets replayed and recreated in companies all across the world. It's the best we know how to do so far until now. And this is really what Quine is aiming to help change. After 7 years of research and development, funded by DARPA, developed in large part in partnership with Galwa, the research lab here in Portland, Oregon, our team at ThatDot has created Quine, a streaming graph. Quine is really meant to address these requirements about how to interpret streaming data, but with new trade-offs, new ways to work with the fundamental problems that are a bit more modernized and can take advantage of some new approaches and new technology. So still handle that high volume of data coming in and produce results with very low latency time requirements. But let's use a lot less RAM, or at least make it customizable so that we don't have to have lots of RAM. Quine removes the need for time windows. So if you're joining data together and you're waiting for a B to arrive so you can join it to an A, you don't have to hope that A and B both arrive within the same 30-second window so that you can join them together. And if they don't, you don't have to give up the fact that you want to join them and lose out on that information. So Quine eliminates the requirements for time windows. It gives us the opportunity to take the work that has been done under the hood for turning the database inside out and start to wrap it back up and package it back up so that we've got these new capabilities and easy to deploy and easy to operate sort of a setting. Take those cap theorem trade-offs that we were forced to implement across the microservice architecture, requiring deep expertise, wrap them back up in the system with a little bit of creativity so that we can handle the failure scenarios that inevitably occur in distributed systems, handle those in a more elegant fashion that fits with modern data needs and modern data architectures. Take this vague and messy question of distributed transactions and come at it from a different point of view to say, let's let the data be the shape that defines what we're going to trigger. And take that out of order dependent, or that order dependent processing, and allow data to come in any order, even backwards if you want to, and still arrive at the right answer of the streaming results that come out. Lastly, take that requirement to be able to look back at old data, and let's approach this from a different perspective. Instead of saying you have to set up a completely separate data pipeline and re-ingest all that data just to get back to the state that you want to inspect. Instead, Quine has the capability to take past data and make it present in a query that you could run over the data as it is right now, or just add a timestamp and say, give me the answer to this query as it was yesterday, or a week ago, or a month ago. So Quine is really aimed at this problem of interpreting streaming data and is a fundamental new architectural component in that world to shift the trade-offs and to do something new in this space, to make it a bit easier to build these systems, a bit more reliable and more effective. It really comes down to two things. To use Quine is to consider the event-driven data and use it to produce data-driven events. By event-driven data, what we mean is you plug it into a streaming architecture, so something like Kafka or Kinesis, a source of data that is going to be an infinite stream of high volume events coming in. Quine takes each of those events and builds them into a graph. That graph data structure is managed internally in Quine, But a user then can set what we call a standing query to monitor the structure of that graph. And every time little components show up in that graph that are an answer to an important question, that produces a data-driven event that is the real-time query result that gets pushed out to another system, or can even be used in more interesting ways, like to call back in and maybe update the graph or trigger some other actions. So event-driven data coming in to build the graph, and then monitoring that to have data-driven events when graph structures appear as an answer to the question that you're looking for. So a level down a little more practically, what that means is that on the event-driven data side, we can solve for that high volume data scenario. So this is kind of table stakes in that we have to be able to consume just a huge amount of data and be able to scale it to very large enterprise levels of throughput. Connect in your Kafka topic, your Kinesis topic, any source of streaming data, or combine it with batch data that you've got produced in a more traditional batch static fashion. Streaming and batch can be mixed together and merged on that event-driven data side. You can join lots of different data streams, and you can let go of the concern about in what order does the data arrive and how do I juggle holding on to part of it while waiting for another part to arrive. Let's banish this notion that you have to have time windows and data arriving within a certain time window in order to be able to join it. Let's add in the schemaless flexibility that a graph enables so that you don't have to set up the data system with an understanding baked in of what questions you want to ask or what data it's fixed to be able to handle. Let's allow new data streams to be able to come in and change and evolve over time. And then, like we hinted at earlier, Quine allows the ability for historical queries to go query what did the data used to be. So since we have data streaming in constantly, it's constantly changing. Let's go back and get it as it was at a fixed moment in time. On the right-hand side, the data-driven events, applications that Quine is already being used for in the marketplace right now include cybersecurity and building the next generation XDR platforms. Graph AI systems are just leaving the research lab, and Quine is the perfect implementation platform for these things. Our team has even built some of these that we offer for a new kind of anomaly detection that we call novelty detection. It uses a streaming graph under the hood to score every piece of data that comes through and report immediately how unusual it is and why it's considered unusual. We've got other users using it for CDN log monitoring or blockchain analysis to look at cryptocurrency and understand what's going on with the transactions under the hood. Monitoring Kubernetes events so that you can see why did Kubernetes decide to auto-scale this particular application, or to build data cleansing pipelines. These sort of data-driven events, the sky's the limit for what can be done here because the system overall is extremely powerful in that it can produce these data-driven events out to other systems, or it can even call back into the graph and clean the data or do other analysis as data flows through. Just to look a little closer at one of these examples, that cybersecurity example tends to be a model for really how all data pipelines work in some sense or another, in that data comes in at this low level of a pyramid. There's multiple types of data streaming through. They're coming in a high volume. And the goal of the pipeline is really to consume that data and start building it up and climbing this ladder of abstraction so that we can talk about not a million low-level events, but fewer sorts of objects that we care about. And those objects combine to form certain events at a higher level that we care about talking about. In the cybersecurity context, we want to find when an attacker is present in an enterprise environment. And so those events might be something like processes started or users logging in or accessing resources. And when we can monitor those and put those pieces together, we can start to understand, do some of those events represent stages of an attack? And if you have certain stages, like an infiltration of a hacker who gets into a system and starts compromising components and expands across the network, and then they're working toward exfiltrating data, we can start seeing those stages in real time as they occur and put them together into the one answer that we actually care about. Is there an attack happening? Let's stop that breach before we lose the crown jewels. That's really the goal of the data pipeline in a security context, is to consume many kinds of data at the low level and then build them up into more meaningful events and produce a small little trickle of information coming out. But that little trickle of information is the high value information, like that an attack is happening now and here's the information about what it is. And of course, here's the obligatory XKCD from just recently, that, you know, if you're going to sit down and go analyze data, the sad truth is you're going to produce more data from it. And more data is actually the opposite of the goal. What we really want to do with our high volume data pipelines is interpret that data so that less data comes out. There's less for a human to work with, but that data is more informative and more useful and more actionable. So this is the goal that Quine is aimed at, and kind of the space in which we operate here. So let's ask this question now. How does it work? Sounds great, sounds kind of pie in the sky, but how does it actually work? Under the hood, we built Quine from the ground up to address graph structured data. The reason for that is because graph structures of data are really a superset for all the other kinds of data. We're used to working with tables like in relational databases, or trees, like your JSON data is structured as a tree, or MongoDB, you know, your document store is storing it as a tree, or maybe you've got key value stores, you know, really just maintaining a list of keys that can map to their values. But there's a progression here, and a mathematical progression, where in the diagram on the left, each of these higher structures can represent the lower structures. And if you've worked with relational databases, you might say, but I can simulate a graph in my SQL database. And that's true, but you pay for it with processing, with additional computation. And so representing the data natively in a graph gives us extra abilities to then work with that data without having to spend extra computation like on joins across tables that then slow the processing down and force us into old style trade-offs. So the graph data model is really at the heart of what we're doing. And for Quine, it's a property graph. So nodes in the graph are objects, and edges between them are essentially predicates. So that structure of data maps very nicely to what we think of really just as natural language, where you take objects and can refer to them with a predicate in between, like the Legend of Zelda, or the legend isn't named after Link, but Link explores Hyrule. You can take everything that you would just describe in natural language, and there's a very direct representation in the graph. So it is both flexible and powerful because that subject predicate object relationship from natural language corresponds directly to that node edge node pattern that makes up a graph. What's unique about Quine is that we took that graph data model and we paired it with a graph computational model. Under the hood, each node in the graph is backed by an actor. And that actor it's built on an old idea from the 70s, Carl Hewitt's model or actor model. The idea is that each actor is a very lightweight computational unit. So one actor can perform arbitrary computation in a single threaded fashion, and it communicates with the rest of the world, including other actors, exclusively through message passing. So an actor encapsulates some state and sends messages to other actors or out of the actor system. So that asynchronous model is perfect for representing a graph in Quine. So when a query is run on Quine, it turns into messages sent between nodes, traversing edges that connect those nodes. So this whole system is built in Scala on top of Akka, which is a battle-tested, tried and true system used in enterprise environments. across the world. Akka is an excellent implementation of the actor model, and we really appreciate the work from that team and all the work that they've done over the last 10+ years in building and maintaining and releasing Akka and that implementation of the actor model. So one other foundational component built on Quine here, since we've got a graph data model paired with a graph computational model, the storage model under the hood builds on each individual node. That node saves its data to disk with a technique called event sourcing. So an update comes into a node saying set a new property or create an edge pointed at this other node, and the node, backed by an actor, is able to very quickly and efficiently test, does this instruction to change the value, does it have an effect? If it does, then save only that delta to disk. Add it to an append-only log of changes that is the history of this one particular node. So in memory, we've got the materialized state of that node's current status, and it is computing all the small little changes that need to be saved to its history, and it's adding those to an event log on disk. That gives us a very fast way to save changes that performs like a write-ahead log. It's just such small little changes that we can do it very quickly, save them on disk, and the node can continue going about computing other answers to queries using its in-memory cache state. This is what we call semantic caching, where we can use the structure of the data and other facts about its computation to choose what we keep in memory and make it fast and efficient across the board. That data stored on disk has many different options for how it's actually stored under the hood. So Quine implements that graph computational model and that graph data model on top of other technologies for the actual data storage. Technologies like Cassandra and RocksDB, Hydraulics or Amazon's S3. We've got a number of different swappable data storage layers. So if your team is using one particular data storage technology, and it's important for your ops team, for example, to keep using that technology can be used as the fundamental data storage layer that Quine uses to communicate with and save data while still providing that streaming graph on top of it. Ultimately, the data storage layer really just needs to produce a key value storage model. So internal to Quine, Quine does all the translation between everything it needs, saves data in that key value store model, which changes a little bit depending on the actual storage technology, so we can tailor it to the capabilities of the underlying system. But it's ultimately really just a key value store. And Quine supports using local storage like RocksDB running on the same system that Quine is running on, or remote storage like Cassandra that can be used in production data pipelines with resiliency and failover to ensure that data is always available and properly stored and replicated to many different places. So these are the fundamental building blocks that Quine is built on top of. And probably, maybe some of these are new, but some of them are probably familiar also. Event sourcing is an old technique. The graph data model has been around for a long time. These data storage technologies are very solid and in use all over the place. So these are really the building blocks and the pillars that Quine is built on top of. But in addition to these fundamental technologies, we did a few crazy things too for Quine. And the idea here is really just that if you only, this great quote from Henry Ford, if you only do what you've ever done, then you only get what you've always got. And so if we're always walking the same path for how we solve some of these fundamental stream processing and data storage challenges, if we're always solving them the same way, we always end up with the same trade-offs. The goal behind Quine was to really start with these fundamental pillars and plunk us down in a different part of the landscape at the very beginning of it, and start covering these same fundamental challenges about data storage, stream processing, and so on, confront these fundamental issues, but with the new capabilities that we build along the way, starting from a new, unusual place, so that we can have different trade-offs and produce different kinds of results. So we've made some design assumptions and baked them into Quine that might sound a little bit crazy. First, let's start with a stateful system that is planning to consume an infinite amount of data. So let's store data so that we can eliminate this time windowing problem. We can join all data together, whether it was streamed in nanoseconds ago or arrived months ago. Let's combine that real-time event with very old data so that we can interpret it correctly. And then Quine under the hood bakes in this idea that you don't have to create a node in the graph. Instead, let's flip that assumption around and just say all nodes exist. Every single node exists. It just doesn't have an interesting history saved for it. So if you want to refer to a node in a streaming sense, that node is there and waiting for your query or waiting for properties or edges to be set on that node. You don't have to create it. It just always exists. The only thing we actually store to disk are interesting changes to its history. So it ends up being very easy and inexpensive for us to assume that all nodes exist, and every node that you can refer to will be there when you want to refer to it. Nodes themselves are uniquely defined by their ID. And so we've created multiple different ID providers so that you can have different kinds of IDs for a node. Maybe you just want a simple number for each node. And so its ID is just a simple number. Or maybe you want something a little richer. You want to use UUIDs to refer to nodes. Maybe even something complex, like a custom class that allows you to namespace certain kinds of data in the graph and keep it separate from other portions of the data. These kinds of things are all built into Quine, and we've built a function that we call ID from to use in a graph query that makes it easy to query and refer to nodes by their IDs and really use the values that we care about and let Quine translate that into what that means for a node's ID under the hood. So I'll show you an example of this in a minute. But first I want to answer this question about why. And of course the answer is because we want new capabilities. We want to move past the traditional trade-offs of stream processing systems that we were talking about early on, because they lead to slow and hard development when building these microservice systems. So the kinds of capabilities that we can bring to the table now, just to start scratching the surface, is we can issue very rich queries, graph queries on that very richly structured graph data. So our team has built a custom compiler for compiling Cypher queries for stream processing, really. So you work with Quine via Cypher queries. As data comes in, that data is passed to a Cypher query that can be used to construct the graph. And then you can monitor the structure of the graph similarly with just a Cypher query. Under the hood, our system turns that Cypher query into an abstract syntax tree, an AST, that can be dropped into the graph and propagated around through the actors under the hood. Second, not only can you query the current moment, but as I was mentioning before, you can query the past. What did the data used to be like? All you need to do is take that same query that you would issue for the current moment and add a timestamp. What did this data look like, when time equals 4 or 7 or 10? Those historical moments mean we can go to exactly the right nodes and replay them up to that moment in time and use their state at that moment in time to answer their part of the query before continuing to recurse and do that pattern elsewhere in the system. So the net takeaway there is really just a mastery of time where you can query not only the present moment, but also how the data used to be at any moment in the past. But let's round out this triad and say you query the present, the past, and using a technique that we call standing queries, you can even query the future. This is really the data-driven event production process. A user can issue a Cypher query and say that this query is a standing query. As a standing query, it is added into the graph and now lives inside the graph. Quine will handle where to propagate that query to and where to start it inside the graph, and then it gets relayed from node to node. Its small little incremental part of the next step of the query gets automatically pushed through the graph, so that the query might be issued a long time ago, living inside the graph, new data streams in and is changing and updating the graph. Well, that new data is progressively inching toward matching the pattern that we care about. So as the data changes, small little units get automatically propagated through the graph. And as soon as the data structure matches what we're looking for, it instantly turns into a match sent out to the next system, or otherwise triggering the desired action that comes next. And this is really how we accomplish this goal of eliminating this notion of time windows. So take the durable stored data represented as a graph and monitor it live for certain patterns that we care about. So you don't have to specify your pattern and worry about it, the process of joining these together. Instead, you just describe the shape of the data that you want to find. And as that shape changes and evolves and gets built over time, it instantly turns into a result sent out to the next system or triggering any other action that you'd like. But you don't have to take my word for it. Let me show you a demo. So I'm going to drop out of the slides here for a minute and go to Quine.io. Quine is an open source application available at this website up here, Quine.io. And if you go there and click download, you'll see you can download a jar file for running Quine itself. You could also run it from Docker if you'd like. I'm going to run this jar file as it downloads on my system, and I'm going to run it with a recipe. Recipes are configuration packages. So they're the definition of what you might do for one particular use case, contributed by community members and available to anyone who wants to use them. I use a recipe just by looking around and choosing the one that I want. In this case, let's do this Ethereum tag propagation example. I can take this recipe defined up here with just the YAML syntax that defines what data I want to ingest. So this defines two ingest sources and gives me a standing query to monitor the output, and then also sets a few things around node appearance and some built-in quick queries and some other features about using the UI for the system. So I'm going to run this recipe just by taking this command right here, and I'm going to paste it into my terminal. And I'm going to throw an error here just to illustrate a little temporary situation. We are waiting for a new release of RocksDB that supports M1 Max. So if you have one of Apple's new M1 processors, it's not quite ready to use RocksDB yet, but we have this additional storage type where you can specify using MapDB instead of RocksDB. So I get a warning message when I try to run this. It throws an error, but it tells me what to do and what to fix. So I'm going to run that same command again. Let me clear out this text, but I'm going to say -d and paste in the option that I got from that error message, which is to say have Quine use the storage type of MapDB. And then since I'm running a recipe with -r Ethereum, I'm also just going to add a statement at the end to say force using this particular configuration that I'm specifying in the command line instead of only relying on the recipe. So this lets me specify the storage layer myself. So when I run that, it executes the recipe and walks through the process of starting up the Quine graph and setting node appearances and quick queries and so on. It sets up the standing queries and it starts two ingest streams. Then I have a web server running already, so I can go look at what's happening, and I'm starting to get some output here as well, so you can see it updating with some results. But let's go to that URL that the web server is running at. I'm greeted with an empty canvas where I can explore the graph. We'll come back to that in a moment. Over here on the left-hand side, I've got built-in documentation through Swagger documentation where I can easily see What do I need? What's the schema for defining an ingest stream? What sources are available? We're using this server sent events example. But I can define all that and even use it here in the REST API, or use the REST API from the interactive documentation. And lastly, there's a simple monitoring dashboard also built in, so I can see what's the current status, how's it running, how's the memory usage, how many nodes do we have currently in the system right now, and just get a quick overview of some of the system state. So let's go explore this graph. Our recipe set a couple sample queries that we can use up here to get started. I could type in other Cypher queries up here to do something ad hoc. But this example pulls out some of the recent blocks. These blocks are coming from live Ethereum data, so I don't really even know what's in them. They're just whatever is happening right now as the Ethereum blockchain is being built and transactions are being processed. So the recipe connects to a server that just publishes the current transaction state for the Ethereum blockchain. And we could go inspect any of these blocks. If I mouse over one of these, you can see its properties have been set on each individual node. Those properties come from the incoming JSON records or the incoming records being streamed in. And if I right click, I have some convenience functions here or some convenience queries for exploring the graph. I'm going to do some exploration of the graph just to get a sense of what this looks like. This is the account that actually mined that particular block. Here's a collection of all the transactions in that block. That's a bunch. Let's just pick one of these to explore. This transaction down here came from this account to this other account, which you can tell was also involved in some of these other transactions. But we've got a transaction from an account here to an account over there. And so far, this is really just building the graph. So this is the event-driven data side of Quine. So to take in a stream of events and build a graph. But let's have some fun on the other side as well. If I wanted to say I've been following the news and reading about the money laundering case from hackers who had stolen a bunch of cryptocurrency, sat on it for a few years, but then wanted to launder the money so that they could eventually turn it into something they could spend. That sort of a use case becomes trivially easy to do using Quine, because all I have to do is pick an account that I'm suspicious of. Let's just pick this one. Apologies to whoever actually holds this account, but just for a demonstration here, I'm going to right click it and mark it as tainted. This is all built into the recipe. It matches this account style of node and gives me a few more options. I'm going to mark it as tainted. And you can see I immediately got some results out here in the console. Those results come from, let's refresh this so we can see it a little better. Our pink account that got marked as tainted, if we look at its outgoing transactions, it sent a transaction in this way over here to this account. This account is now marked as red and has a new value set on it because it received money from that tainted account, the one that we were suspicious of. So that will keep propagating behind the scenes to as new transactions are made, new results will show up in the console, just alerting me that the tainted money is now moving through the network. And the value on this node tells me how far away it is from the original account. I'm going to pull up a second instance of this and look for a slightly longer example. So in this case, it is this is two transactions, but where a transaction came from this first account to this next one, and then a transaction from there to this next account. So in this case, we pin these to the graph so they don't move around. Let's mark this guy as being tainted. Oh, we got a whole lot of results. And let's select everything and refresh. You can see the pink one is our tainted 0. And then these red accounts have received money. And we could explore by clicking any outgoing transactions to find any other accounts that also received money. So each of these other accounts has the results automatically propagated via standing queries running on the graph, and they update the values and say this account is 2 hops away from the original tainted one. And so we can mark and trigger and monitor the graph itself and automatically find where this money goes, what's happening with it, and instantly get notifications that are very informative. They tell us how far away the newly receiving account is from the originally tainted account, all done via ingest queries that constantly stream in new updates to the graph, and a standing query which then monitors and propagates those changes through the graph automatically behind the scenes. So that's a fun little example. There are lots of other use cases that users have been putting this toward. But I want to kind of look toward wrapping up this particular talk and answer any questions. Maybe just starting with one last question to say, where does this fit into the enterprise data infrastructure? So if you look at a kind of a schema of an existing enterprise data pipeline, you've got data sources like Kafka feeding what really amounts to custom business logic. And so those custom business logic units could do all sorts of things. They're serving IDs, they're processing data, they're storing data and retrieving it. All sorts of things happen in a data pipeline. And the most natural place is to look for some custom business logic, maybe an old system that needs to be replaced or some new functionality that needs to be added to that data pipeline, and say, instead of writing a whole lot of custom business logic for this one component, let's use Quine and just wrap it up with ingest queries and a standing query. And then that standing query can propagate its data out to the next systems in the pipeline. So it makes it very easy and gradual to consider how Quine can fit into existing data pipelines. And then the team itself can make a decision about where else to use Quine. Maybe it's useful in multiple places through a data pipeline, or maybe it's just one critical problem that we want to go try to apply it to. So that sort of gradual integration for one problem at a time is a very natural application of Quine. And Quine is built to be highly scalable. It's back pressured, so it will remain resilient and functioning under heavy load and consumption of all available resources. So it'll remain responsive. It has a very small footprint. It can automatically scale up to run faster on bigger machines. You can add and modify streams over time. So it's meant for enterprise infrastructure to grow to very large scales. So just to review real quickly, the event-driven data side of this lets us focus on the shape of the data and not the order of operations. So you don't have to think about in what order must events be processed. Instead, you just say, take the data in, build it into a graph structure that is very expressive, and it's flexible and fast. And let's forget about this notion that you can only match data when it arrives within a small little time window. Pairing that event-driven data side with the data-driven events means we can monitor that graph, and the data structure itself causes new events to flow out of the system. Those new events can be sent downstream to the next item in the data pipeline, or you can call back into the graph and update values. So use it to clean data, use it to enrich data. It can fetch and feed more data into the system. That mechanism is just very expressive and very powerful. And overall, that gives us the new capability for interpreting high volume data in real time in this highly expressive way. Our mission is to take high volume data and turn it into high value data. So regardless of the kind of data that you have or the number of sources, consume that data, build a graph, monitor that graph for informative data structures using an expressive query language, and then take every one of those results and send it out to the next stream to handle it, or call back into the graph and trigger any actions that you want. And I'll close with really just one last insight that our team has discovered over our years worth of work creating this system. It's really that graph databases have been around for a long time, but they've been pretty limited and they're kind of known in the industry for being interesting but slow. So you can't really use them for high volume use cases. So they might be fun, but you'll never be able to scale them. What our team discovered is that there's really something that's been missed over the last decade worth of research and development on graph systems. And it's really that graph's killer application that has gone unused up until this point in time is incremental computation. Quine's ability to take a query, decompose it into an abstract syntax tree, and then automatically propagate it through the graph at the ideal moment when it is the fastest and cheapest to do that work, and where we can use the structure of the data to inform where the query should go next, we can entirely avoid this question of when should I run my query? And, has the data changed? Is there an answer worth getting out of the system right now? All of that gets wrapped up and built inside of this event-driven graph. And that is what we call Quine. So you can see more at quine.io. You can download it and use it. We'd love to hear stories about how it's being used, or if you have any questions on how to use it, come find us on Slack. Our engineering team is available to help answer questions and talk about it. You can go look at the code on GitHub. Quine is supported by that. And so enterprise users who want help scaling it for just massive workloads, or have other questions and want some support for running it, please let us know. We're happy to help, and our team is hiring. So if any of these sound like fun ideas to you and you're a distributed systems engineer or data engineer or compiler engineer, or any of this sounds fun to you at all, drop us a line and let us know. We're looking to add more great team members to our team. So with that, I will wrap up and want to say thank you for your attention.